Welcome back, Chem 20s, to part 2 of combined gas law. I've got two special examples keyed up here that are going to help us in the long run when it comes to understanding this concept. So let's look at example number 3. Use the combined gas law to explain why the temperature of a gas tank goes down when pressure is released. It is assumed that the amount of gas in the canister is identical since the volume of the gas tank does not change. So this is going to be key. If you think about certain objects like a balloon will get bigger or smaller, let's say if we change the temperature, right? If it's hotter outside, it's going to expand that little bit. The volume's going to have more spaces between the particles. Well, this is true in a car tire. When summer's over and we get that first blast of winter, you need to look at your car tires because a lot of them are going to be underinflated because they are going to decrease the volume, and you need to fill them up with some air so that you're not going to damage your tires. Well, the difference between a tire and a gas tank is a gas tank will not change volume. Think about this. On a hot day, your propane tank on your barbecue doesn't get bigger. On a hot day driving down the highway, a tanker truck, that tank in the back, doesn't get bigger because it's hotter outside. So this assumption for a gas tank makes sense. Whatever our initial volume is, it's going to be exactly even or equal to my final volume. So whenever I get to make up a number, I always make up something easy. You could pick any number you want except 0 because your volume, there's got to be some volume whatsoever. So I like to pick something simple like 1 liter. You could pick 10 liters, you could pick 50 liters, but I try to stay away from big crazy numbers like 14.26899999 liters. It just doesn't make sense to use it. Now, we are trying to prove why temperature goes down when pressure is released. So that means my pressure is going to go down as well. So I'm going to make up two pressures here. And again, I'm just going to make up numbers that are nice numbers so we can see if there's any sort of pattern. So I'm going to make up, let's say, 100 kilopascals. It says pressure is released. So my second pressure is going to be less. So I'm going to make it half as the amount, 50 kilopascals. And we're trying to explain why the temperature of this tank also goes down. So let's pick a nice T1 value. So I'm going to pick 100 kelvins. And let's try to calculate T2. Let's prove. Ideally, it says we know it'll go down. So let's just prove that point. So we have our formula, P1 V1 over T1 equals P2 V2 over T2. Again, we're trying to prove temperature, so we're going to move it up to the other side, which means these guys are going to exchange places, and so we'll have to move T1 up. So our formula is going to be T2 equals T1 P2 V2 over P1 V1. So let's substitute in our numbers. We're going to take 100 kelvins and we're going to multiply by 50 kilopascals, and we're going to multiply that by 1 liter. We will then divide the whole thing by 100 kilopascals and also 1 liter. Now, notice how this formula works. Because the volume is constant, a tanker tank will not change volumes. It's locked in. Whatever number you pick here, as long as it's not 0, it's going to cancel off. And so when I go to calculate this, we're going to take 100 times 50 divided by 100. And I think most of us could do this in our head. This is going to be 50 kelvins. Now, I picked nice numbers. We could have picked crazy numbers. We could have picked numbers with decimals. But I wanted you to see something here. So when my pressure went down from 100 to 50, when we released pressure, my temperature went from 100 to, my temperature also went down. Well, if you think about it, since my volume is the same and it's going to cancel out anyways, if we came back here and said, hey, let's get rid of volume, If you look at how this formula sets up when my volume is constant, so it more or less cancels itself out, this formula has the same format, P1 over T1, that Charles' law had, where if one variable goes up, the other variable goes up. And if one variable goes down, the other variable goes down. So, of course, we would expect that if the pressure goes down, the temperature would also go down. And that's what I want us to realize. When the volume is constant in combined gas law, we're going to notice that there's a direct proportionality, or they are directly proportional between pressure and temperature. That's what this question is trying to show you. Now, the fourth question we're going to do is we're going to have you pick some numbers. Now, you'll notice we're going to do this question twice. I'm going to do it once, and we're going to use my numbers. And then I want you to go off and do it again yourself, but pick nice numbers again. But again, be a little bit more creative than the numbers I'm going to choose and prove that you get the same answer every single time. So the question says, if the pressure and the volume of a gas is tripled. So again, they don't give me the numbers, so I'm going to make them up. So I'm going to pick 1 kilopascal. And for my second pressure, it's got to be tripled. So this is going to be now 3 kilopascals. For volume, I'm going to pick 1 liter. For my final volume, I have to triple it. So that's 3 liters. Again, the only value you can't use is 0. What will happen to the temperature? So we're trying to figure out temperature. So again, I'm going to pick a temperature. I'm going to pick 1 Kelvin. Okay. What are we going to see happen for the final temperature? Well, again, let's set this guy up. P1 V1 over T1 equals P2 V2 over T2. We have now solved for temperature in the denominator quite a few times, so I can just automatically do this. T2 equals T1 P2 V2 over P1 V1. So we're going to sub in 1 Kelvin times 3 kilopascals times 3 liters. I can hear my cat. Divide by 1 kilopascal. Divide by 1 liter. So I don't think we need a calculator. 1 times 3 is 3, times 3 is 9. Divided by 1 is still 9. Divided by 1 is still 9. And this is going to come out in kelvins because kilopascals cancel, liters cancel. So what we're supposed to do is, what do you notice happens to the temperature? When we triple the pressure, when we triple the volume, my temperature goes from 1 Kelvin to 9 kelvins. So it looks to me like temperature is 9 times larger. Now, I chose nice numbers, so this was easier to see. I would like you to try the question again, go back, and I don't care what you pick. You could pick 15 kilopascals, 45, triple it. You could pick 10 liters, 30 liters, triple it. You could pick 2 kelvins for all it matters. See if your number is 9 times larger every single time. Let's check out how you do on this.